today I will be talking about time-dependent multi-state switching of antiferromagnetic order parameter in manganese 3 tin. It's a very different topic compared to the last two talks, but I hope I can give you a very brief introduction to what's going on, and then hopefully you get to see more of what I've done. So what we're interested in is this particular antiferromagnet. It's called manganese 3 tin. It has a very unique spin structure to create what is known as an octopole moment. And we will be introducing how you can switch this antiferromagnet just by applying current pulses. So for this, we need what is known as spin orbit torque switching. And we will go into how you can see the anomalous Hall effect, which is very rare in an antiferromagnet, how you can switch it, the mechanism of switching, and time-resolved measurements during the switching. So what we need is a Hall bar. So we make thin films of our antiferromagnet with a heavy metal on top and make them into these type of Hall bars. I mean, this is a typical ferromagnet, right? You measure the anomalous Hall effect, which is proportional to the magnetization. So if the magnetization is up or down, you have a positive or negative anomalous Hall effect, for example. What people showed is that when you have a ferromagnet on top of a heavy metal, you send a charge current through this bilayer. What happens in the heavy metal is because of spin orbit coupling, the charge current gets converted into a transverse spin current, which then moves into the ferromagnet and then causes a spin torque to act on the ferromagnet, and then you have a switching of the ferromagnet. So typically, you initialize it in an up or down state, and when you apply DC current pulses, you can move from up to down depending on the current polarity, and the direction of the switching is different depending on whether you apply a small magnetic field along the current direction or against the current direction, which is needed for deterministic switching. So in ferromagnets, you typically encode information, let's say in 0 and 1, which could be up or down. In an antiferromagnet, you could probably encode some information in orthogonal directions. In this case, it's a collinear antiferromagnet. And typically, these occur in a time scale of 210, or this is the fastest time scale observed in ferromagnets, around 210 picosecond. And in antiferromagnets, what has been experimentally observed is 100 picoseconds, while they expect the dynamics to be much, much faster in terahertz regime, and a lot more robust than ferromagnets, which is why antiferromagnetic spintronics is interesting. However, there are a few issues, right? So in some of the most well-studied antiferromagnets, in this case, we have copper manganese arsenide and platinum manganese. If you are to send current pulses into this material, you can switch from up to down, but the switching amplitude is only 10 milliohm, which is really small. So essentially, you cannot make something, maybe a realistic device for applications. I mean, the readout's really weak, the switching percentages are really small, and they're really hard to image in order to confirm that what you're switching is magnetic. There's complicated geometries, and you need high current density. So you want something a bit better. So that's where we have this material, which is called manganese 3 tin. Despite being an antiferromagnet, it has a large anomalous Hall effect. And what people have shown in a few groups in Japan is that you can switch this by depositing a heavy metal such as platinum or tungsten on top, and you send a current, you have spin orbit torques. This leads to switching. And this kind of switching is at least an order of magnitude more than what you observe in typical collinear antiferromagnets. And you can switch at a relatively reasonable current densities. And recently, they've shown that even 50 or 100% of the antiferromagnet can be switched by this method. So we want to see how fast it is and whether it's really better than ferromagnets. Is it actually terahertz dynamics? This is one of their questions. So in order to do that, we prepare polycrystalline manganese 3 tin by DC magnetron sputtering, co-sputtering at room temperature. Then we anneal it in an argonaut in vacuum for 1 hour at 600 degrees. And then we deposit a heavy metal layer on top. If you look at the X-ray diffraction spectra, you see that you have a nice polycrystalline film with all these different peaks, each of which corresponds to different grains of the manganese 3 tin. And then we pattern this thin film into two different devices, so one of Hall bars and the other of Hall crosses. One we use for switching, the other we use for time-resolved Hall effect measurements. So if you want to look at the crystallinity of this material, we have a high-resolution TEM image, and you see that there is a nice big grain that is very columnar. It goes from the bottom of the from the substrate all the way to the top. And if you look at it if you take a closer look, you see that it's very nicely ordered within these crystals. So even though it's polycrystalline, it's quite nice for experimental purposes. So what is the antiferromagnetic order parameter in this material? So on the left, you see a spin structure. So this is one of the ground states, and you see these 6 manganese atoms that are all pointing in different directions. And the green arrow in the middle is what is known as the octopole vector, which is the order parameter. So in typical antiferromagnets, you have the Nel vector. In this case, you have the octopole vector. And you have an anomalous Hall effect if there is a projection of this octopole vector out of plane. So you have a negative anomalous Hall when it's pointing down, a positive anomalous Hall when it's pointing up, and 0 when they are pointing in plane, which is also another ground state. And this is despite the fact that the magnetization is really small. So in these films, magnetization is 2 emu per cc, which would be almost 100 times or 1,000 times smaller than typical ferromagnets like cobalt, iron, boron, or cobalt even, which is very impressive in this case. So we want to switch it, so we apply a current density along this Hall bar in the presence of a small magnetic field, and the pulses have a rise time or a fall time of 420 nanoseconds. And in this case, what we observe is nice bipolar switching. So it goes from an up to a down state, which is very similar to what you would observe in a ferromagnet. However, we saw something really weird. If we use a different pulsar with really short fall times, the switching behavior is completely different, where you reach these intermediate states which correspond to either an in-plane state or a multi-domain state. And this is very interesting and also a bit weird for this kind of switching. So we wanted to observe it more. So what we did is we have a little circuit. So this is our typical switching circuit. You have a device that is pulsed from V plus to V minus. And then if you add a capacitor, you can vary the fall time or rise time of the pulse generator. And what you see is that if you go from really short fall times to really long fall times, you observe a gradual change from this tri-stable switching to the typical bistable switching that you have seen. Which means that a very different process is involved that includes also the temperature, which has not been observed before in ferromagnets or in antiferromagnets by spin-orbit torque switching. So we come up with a little hypothesis, where we show that we have these 2 different pulses, and depending on whether during the cool down, so when you apply a pulse, during the pulse you reach a temperature that is close to the Nel temperature of the antiferromagnet, which kind of demagnetizes the material. And when during the cool down, so when the pulse stops, your spin-orbit torque is still acting on the magnet. So depending on how fast or how slowly you cool in comparison to how fast the pulse falls, you have a different switching behavior. So to demonstrate an example of how this would happen, we take one of these tri-stable switching conditions, where we start at the intermediate state, so at 20 volts, and then we pulse in steps of 5 volts, in steps of 2 volts, and in steps of 1 volt. And what we observe for the green curves is that if you go straight from 20 volt to 10 volt, you observe no switching, even though the spin-orbit torque should be active. And if you go from 20 to 10 in steps of 2, you observe something in between. And if you go in steps of 0.5 volt, you observe a full switching of the well, as much as you can switch the material. Which means that you have a step-by-step switching where the critical current density for the different grains in the material depends on how quickly you can reach the Nel temperature of that particular grain, or blocking temperature for that particular grain. And the spin-orbit torque needs to be strong enough to exert an effective field to switch the antiferromagnet. So how fast is this reversal mechanism actually? So there is a group in Japan, some of our collaborators on a different project, that showed that because you have these 6 different ground states of the octopole vector, during the pulse, when the spin-orbit torque is acting, this octopole vector is constantly rotating like a wheel. And when you turn off the pulse, it stops at a certain ground state. And they demonstrate this also by simulations where they see that if you look at the magnetization of one of these spins, it goes through all these little oscillations during the pulse, which means that it really goes from up to down to intermediate state during the pulse. So we wanted to see if we can really observe this in real time. And for that, what we want to do is measure the anomalous Hall effect during the pulse. To do that, we use a specific geometry of a Hall bar. So in this case, we have this Hall cross, and we send a pulse that is split into two different paths, such that you can measure the anomalous Hall effect during the pulse. So on the right-hand side here, you see set, reset type of measurements. So you pulse positive volts, negative volts, positive volts, negative volts, and you go from up to down to up to down to up to down for 2 different magnetic fields. So the blue color is for positive magnetic fields and the orange is for negative magnetic fields. And what we observe is that, so we try to measure the anomalous Hall effect during the little blue transition there. And what we observe in real time is that the resistance state starts at a high state, and during the pulse, it goes to an intermediate value of 0 volts. So it looks like the sample is basically demagnetizing during the pulse. And for the opposite magnetic field, you start at a different initial state that corresponds to one of the other ground states. And during the pulse, in the same time scale of around 35 nanoseconds, you observe that it also goes to this intermediate state, which is also true if we observe it in, so the previous measurement, it was done if you average many different pulses together and you measure it during all of these. But down here below, we see single shot measurements, so really during one pulse, and we see qualitatively very similar curves where depending on the magnetic field, you have a reduction or it goes to the intermediate state during the pulse, which makes sense, which corresponds well to our hypothesis that during the pulse, you are essentially reaching the nail temperature of the grain that you're switching. And then during the cool down, as soon as the antiferromagnet goes below the nail temperature, the spin-orbit torque acts very efficiently to switch it from whatever state it is in to a deterministic up or down or intermediate state during the switching. So I very briefly introduced what kind of spin-orbit torque switching can be used to reorient the order parameter on antiferromagnet, switching of antiferromagnetic order with this method, growth of manganese 3 tin, and how you can measure the anomalous Hall effect, and how the switching of the octopole vector in this material is really time dependent, which is an interplay of the temperature and also how strong your spin-orbit torque is when you're pulsing through this. And for the first time ever, we have measured an antiferromagnet using a time-resolved measurement, which is quite a challenging task, not just in antiferromagnets, but also in ferromagnets. And we show that it has this unique temperature and spin-orbit torque dependent switching. And with that, I would also like to thank all the people in my group and Professor Pietro Gambardella, and also our collaborators at EMPA who did the TEM measurements for us. And thank you.
Thank you very much for your interesting talk. So please raise your hand if you have questions. Sorry, probably I missed it, but what is the thickness of these thin films and what is the near temperature for this material?
So the thin film is 50 nanometers of manganese 3 tin with 7 nanometers or 5 nanometers of platinum on top. So it's quite thick. So it's actually quite impressive that you can switch an antiferromagnet that's 50 nanometers thick. And I'm sorry, what was the second question?
What is the nail temperature for this
Yes,
material?
so the nail temperature is 420 degrees, 420 Kelvin.
Mm-hmm.
And in our case, during the pulses, we measure that we can reach very easily 420 or 450 Kelvin during the pulses. And of course, if you go down in pulse lengths, this changes a lot. But in principle, if you have a mixture of different grains with different like blocking temperatures, you're always demagnetizing some of the grains, and these are the grains that switch, basically.
Yeah, okay. Thank you very much. Thank you very much again. So probably...
Yes. Thank you very much.